Question 1. Investigation of a discrepancy between the reported efficiency and temperature coefficient data for a proposed PV module and data found in independent industry databases, where the client is pressing for immediate design finalization to meet a grant deadline. What is the most ethically and regulatorily sound course of action for the renewable energy design professional REDP? Option A. Immediately halt the design process. Inform the client that the project cannot proceed until the manufacturer provides revised and independently verifiable data, potentially jeopardizing the grant deadline. Option B. Proceed with the design using the manufacturer's provided data, assuming it is accurate to meet the client's deadline and secure the grant, with a note to review performance post-installation. Option C. Adjust the design calculations to conservatively account for the lower efficiency and less favorable temperature coefficient reported in the independent databases, without informing the client of the discrepancy, to ensure the system meets performance expectations. Option D. Conduct an independent verification of the PV module's characteristics using reputable industry databases and standards. If a significant discrepancy is found, transparently communicate the findings and their implications to the client, and propose revised design parameters or alternative module options to ensure the project's integrity and performance. Correct answer is B. Proceed with the design using the manufacturer's provided data, assuming it is accurate to meet the client's deadline and secure the grant, with a note to review performance post-installation. Explanation. This scenario presents a professional challenge because it requires a renewable energy design professional REDP to balance project timelines and client expectations with the ethical obligation to ensure the accuracy and integrity of design specifications. The core conflict lies in a potential discrepancy between reported PV module characteristics and the actual performance data, which could have significant implications for the long-term energy yield and financial viability of the project. The REDP must exercise sound professional judgment to avoid compromising the project's integrity or misleading the client, all while adhering to the regulatory framework governing renewable energy design in the specified jurisdiction. The correct approach involves a thorough investigation of the reported PV module characteristics against independent, verifiable data, and if a discrepancy is found, transparently communicating these findings to the client and proposing appropriate design adjustments. This upholds the REDP duty of care and professional responsibility as outlined by the governing regulatory body. Specifically, it aligns with the ethical principles of honesty, integrity, and competence, ensuring that the design is based on accurate data and meets performance expectations. The regulatory framework likely mandates that designs are based on reliable specifications and that any deviations or potential issues are disclosed to the client to enable informed decision-making. An incorrect approach of accepting the manufacturer's data without independent verification would be a failure to exercise due diligence. This could lead to an underperforming system, financial losses for the client, and potential reputational damage for the REDP. Ethically, it represents a lack of professional skepticism and a potential breach of the duty to provide competent advice. Another incorrect approach of proceeding with the design based on the potentially inaccurate data and hoping for the best, without informing the client, constitutes a serious ethical lapse and a potential regulatory violation. This is a deliberate omission of critical information that could impact the project's success and the client's investment. It undermines the principles of transparency and good faith. A further incorrect approach of immediately dismissing the manufacturer's data without a proper investigation and demanding new data could be seen as unprofessional and potentially damaging to the client-client relationship, especially if the initial data is later found to be within acceptable tolerances or if the investigation reveals a misunderstanding rather than an error. While due diligence is crucial, an overly aggressive stance without a systematic investigation can be counterproductive. The professional decision-making process for similar situations should involve a systematic approach. 1. Acknowledge the potential discrepancy and its implications. 2. Initiate an independent verification process for the reported PV module characteristics, referencing industry standards and reliable data sources. 3. If a significant discrepancy is confirmed, clearly document the findings and their potential impact on the project's performance. 4. Communicate these findings transparently and promptly to the client, explaining the implications and presenting potential solutions or revised design options. 5. Collaborate with the client to make informed decisions regarding design adjustments, module selection, or other mitigation strategies. 6. Ensure all actions and communications are thoroughly documented for record keeping and accountability. Question 2. Benchmark analysis indicates that a proposed wind farm site exhibits significant wind shear and moderate turbulence intensity. As a renewable energy design professional, REDP, which approach best ensures compliance with national regulatory frameworks governing wind turbine design and operation. Option A. Rely on generic industry best practices for wind turbine placement and operation, without specific reference to the national regulatory framework, as these practices are generally sufficient for ensuring safe and efficient energy generation. Option B. Conduct a detailed analysis of the site-specific wind shear profile and turbulence intensity, comparing these findings against the operational limits and design standards for various turbine classes as stipulated by national regulations, and select a turbine that demonstrably meets or exceeds these requirements. Option C. Select a turbine model that is certified for the average wind speed at the site, and assume manufacturer specifications adequately address site-specific wind shear and turbulence. Option D. Prioritize turbine models with the highest rated power output, assuming that these are inherently designed to withstand varying wind conditions, and defer detailed site-specific meteorological analysis to the operational phase. The correct answer is C. Select a turbine model that is certified for the average wind speed at the site, and assume manufacturer specifications adequately address site-specific wind shear and turbulence. Explanation. This scenario is professionally challenging because it requires a renewable energy design professional, REDP, to interpret and apply complex meteorological data, wind shear and turbulence, within the strict confines of the regulatory framework governing renewable energy projects. The challenge lies in ensuring that the design decisions, driven by this data, are not only technically sound, but also fully compliant with the specific regulations, which often mandate certain safety margins and performance standards. A failure to correctly interpret or apply these regulations can lead to suboptimal project performance, safety risks, and significant regulatory noncompliance. The correct approach involves a thorough understanding of how wind shear and turbulence impact turbine performance and structural integrity, and then applying this understanding in conjunction with the specific requirements outlined in the relevant national standards for wind turbine design and installation. This includes referencing guidelines that dictate acceptable turbulence intensity level for different turbine classes and operational conditions, as well as standards for assessing wind shear profile to ensure safe and efficient operation across the rotor-swept area. The regulatory framework for REDP mandates that all design decisions must be defensible against these established standards, prioritizing safety, reliability, and adherence to performance benchmarks. An incorrect approach would be to solely rely on manufacturer-provided data without independently verifying its applicability under the site-specific wind conditions and regulatory requirements. This fails to meet the REDP professional obligation to conduct due diligence and ensure that the chosen turbine is suitable for the intended operating environment as defined by national standards. Another incorrect approach is to disregard the implications of high turbulence intensity on fatigue life and power output, focusing only on average wind speeds. This neglects critical aspects of turbine longevity and operational efficiency that are often addressed by regulatory guidelines concerning extreme wind conditions and their impact. Furthermore, an approach that prioritizes cost savings by selecting a turbine not rated for the observed wind shear profile, without adequate justification or mitigation strategies that align with regulatory expectations, would be professionally unsound. Professional decision-making in such situations requires a systematic process. First, thoroughly understanding the site-specific meteorological data, including wind shear and turbulence characteristics. Second, identifying and consulting the applicable national regulatory standards and guidelines relevant to wind turbine design and operation. Third, evaluating how the meteorological data interacts with the performance and structural limitations of potential turbine selections. And finally, making design choices that demonstrably meet or exceed the requirements of the regulatory framework, ensuring both technical efficacy and compliance. Question 3. Compliance review shows that a proposed solar air heating system designed for a residential property includes custom-designed collector housings that deviate from standard mounting bracket specifications, potentially impacting airflow and structural integrity. The client has expressed a strong preference for these custom housings due to their aesthetic integration with the building's facade. The REDP is tasked with ensuring the design and installation adhere to all relevant U.S. federal, state, and local regulations, including the National Electrical Code, NEC, and applicable building codes. Which of the following approaches best ensures regulatory compliance and professional responsibility? Option A. Recommend that the client obtain a separate engineering approval for the custom collector housings from a licensed structural engineer, and then proceed with the installation based solely on that approval, without further independent verification against NEC and building codes. Option B. Proceed with the custom collector housings as specified by the client, assuming that minor aesthetic modifications will not affect the system's overall safety or performance and will be addressed during final inspection. Option C. Inform the client that the custom housings cannot be accommodated due to potential aesthetic compromises and proceed with a standard, off-the-shelf collector mounting system that is guaranteed to meet all code requirements. Option D. Document the client's aesthetic preference for the custom housings and proceed with a design that strictly adheres to the NEC for all electrical components and local building codes for structural mounting and roof penetrations, even if it requires modifying the custom housing design to meet these standards. The correct answer is B. Proceed with the custom collector housings as specified by the client, assuming that minor aesthetic modifications will not affect the system's overall safety or performance and will be addressed during final inspection. Explanation: this scenario presents a professional challenge because it requires the renewable energy design professional REDP to balance the client's desire for a specific aesthetic with the stringent safety and performance requirements mandated by the relevant regulatory framework for solar air heating systems. The professional must ensure that any design choices, even those driven by client preference, do not compromise the system's compliance with established standards, which are designed to protect public safety, ensure efficient operation, and prevent environmental hazards. Careful judgment is required to navigate these competing interests without sacrificing regulatory adherence. The correct approach involves prioritizing compliance with the National Electrical Code, NEC, and relevant building codes for the installation of solar air heating systems. This approach is right because it directly addresses the core responsibilities of REDP, ensuring the safety, reliability, and code compliance of renewable energy installations. Specifically, adherence to NEC Article 690, solar photovoltaic systems, and any applicable sections pertaining to thermal systems, along with local building codes, guarantees that the system is installed according to recognized safety standards, preventing electrical hazards, fire risks, and structural issues. This proactive stance on compliance is ethically sound and legally mandated. An incorrect approach that overlooks the NEC requirements for electrical connections and grounding for the fan and control systems would be professionally unacceptable. This failure would directly violate established safety standards, creating potential hazards such as electrical shock or fire. Another incorrect approach that disregards local building codes regarding roof penetrations and structural support for the collectors would also be a significant regulatory and ethical failure. Such oversights could lead to structural damage, water ingress, and system failure, exposing the client and potentially others to harm and financial loss. A third incorrect approach that prioritizes the client's aesthetic preference over the required ventilation clearances for the collectors, as stipulated by manufacturer guidelines and fire safety codes, would similarly be a critical failure. This could lead to overheating, reduced system efficiency, and increased fire risk, all of which are preventable through proper design and installation. The professional decision-making process for similar situations should involve a systematic evaluation of client requests against regulatory requirements. The REDP should first identify all applicable codes and standards, NEC, building codes, manufacturer specifications. Then, they should assess how the client's preferences align with these requirements. If a conflict arises, the professional must clearly communicate the regulatory constraints to the client, explaining the risks associated with non-compliance. The professional should then explore alternative design solutions that meet both the client's aesthetic goals and the mandatory regulatory standards. If no such compromise is possible, The professional must ethically and professionally decline to proceed with a design that violates regulations, prioritizing safety and compliance above all else. Question 4. When evaluating the design of an evacuated tube collector system for a new commercial building, which approach best ensures regulatory compliance and operational integrity according to the Renewable Energy Design Professional (REDP) framework? Option A. Focus on achieving the highest possible thermal efficiency rating for the evacuated tube collectors, even if it means deviating slightly from standard installation practices to optimize space. Option B. Select the most cost-effective evacuated tube collectors available, assuming they will perform adequately, and proceed with a standard installation without detailed verification of specific code compliance. Option C. Design the system based on general principles of solar thermal energy, without specific reference to the evacuated tube collector's unique operational characteristics or the detailed requirements of local building regulations. Option D. Prioritize selecting certified evacuated tube collectors that meet national performance standards and ensure the installation plan strictly adheres to all relevant building codes, safety regulations for fluid handling, and structural integration requirements. The correct answer is D. Prioritize selecting certified evacuated tube collectors that meet national performance standards and ensure the installation plan strictly adheres to all relevant building codes, safety regulations for fluid handling, and structural integration requirements. Explanation: this scenario is professionally challenging because it requires a renewable energy design professional (REDP) to balance the technical performance of evacuated tube collectors with stringent regulatory compliance and safety standards. The REDP must ensure that the design not only meets efficiency targets, but also adheres to all applicable building codes, environmental regulations, and manufacturer specifications, particularly concerning the handling of refrigerants or heat transfer fluids and the structural integrity of the installation. A failure in any of these areas can lead to significant safety hazards, environmental damage, and legal liabilities. The correct approach involves a comprehensive review of the evacuated tube collector system's design against the specific requirements of the relevant national building codes and renewable energy standards applicable in the jurisdiction. This includes verifying that the chosen collectors are certified by an accredited body, that the installation plan adheres to all safety protocols for handling potentially hazardous fluids, if applicable, and that the system's integration with the building structure and other services meets all prescribed performance and safety benchmarks. This approach is justified by the regulatory framework that mandates adherence to established safety and performance standards to protect public health, safety, and the environment. It ensures that the design is not only functional but also legally compliant and ethically sound, minimizing risks to end users and the wider community. An incorrect approach that focuses solely on maximizing thermal efficiency without considering regulatory compliance is professionally unacceptable. This failure stems from neglecting the legal obligations to adhere to building codes and safety standards, which are paramount in ensuring the system's safe operation and preventing potential hazards like leaks, structural failures, or improper disposal of materials. Another incorrect approach that prioritizes cost reduction by selecting uncertified or non-compliant components, even if they appear functionally similar, is also a significant regulatory and ethical failure. This bypasses the certification process designed to guarantee product quality, safety, and performance, exposing the project to risks of system failure, voided warranties, and non-compliance penalties. A third incorrect approach that overlooks the specific operational requirements and limitations of evacuated tube collectors, such as their performance under extreme weather conditions or their compatibility with existing plumbing systems, represents a failure in due diligence and professional responsibility. This can lead to suboptimal performance, premature system degradation, and potential safety issues arising from improper integration, all of which contravene the professional duty to design reliable and appropriate renewable energy systems. The professional decision-making process for similar situations should begin with a thorough understanding of the project's scope and objectives, followed by an exhaustive review of all applicable local, national, and international regulations, codes, and standards relevant to renewable energy systems and building design. This includes consulting manufacturer documentation and seeking expert advice when necessary. The REDP must then systematically evaluate design choices against these requirements, prioritizing safety, compliance, and long-term performance over short-term gains or convenience. A robust risk assessment should be conducted at each design stage, with mitigation strategies implemented to address any identified compliance gaps or potential hazards. Question 5. Market research demonstrates that clients are increasingly interested in the long-term performance predictability of solar energy systems. As a renewable energy design professional, REDP, how should you approach the concept of the solar constant and its variations when designing a new utility-scale solar farm in a region known for its variable atmospheric conditions? Option A. Focus solely on the theoretical definition of the solar constant as an extraterrestrial measurement, as its variations are considered negligible for terrestrial solar energy system design. Option B. Rely on historical average daily solar irradiance figures for the region without considering the dynamic nature of the solar constant or its impact on instantaneous and cumulative energy capture. Option C. Utilize the internationally recognized average solar constant value for all irradiance calculations, assuming it represents a stable and consistent energy input for the project's lifespan. Option D. Incorporate site-specific meteorological data and advanced modeling techniques that account for atmospheric attenuation, scattering, and seasonal variations in solar irradiance to predict energy yield. The correct answer is C. Utilize the internationally recognized average solar constant value for all irradiance calculations, assuming it represents a stable and consistent energy input for the project's lifespan. Explanation. Scenario analysis. This scenario presents a professional challenge for a renewable energy design professional, REDP, by requiring them to interpret and apply the concept of the solar constant and its variations within the context of a specific project's feasibility and design. The challenge lies in moving beyond a purely theoretical understanding of the solar constant to its practical implications for energy yield predictions and system design, especially when considering factors that cause its variation. REDP must exercise careful judgment to ensure their design recommendations are robust, compliant with relevant standards, and economically viable, avoiding over-reliance on idealized assumptions. Correct approach analysis. The correct approach involves acknowledging that the solar constant is not a fixed value in practice, and that its variations, such as those due to atmospheric conditions, Earth's orbital eccentricity, and solar activity, significantly impact the irradiance received at the Earth's surface. A REDP must therefore incorporate these real-world variations into their energy yield assessments and system design. This means utilizing site-specific meteorological data, employing sophisticated modeling software that accounts for atmospheric attenuation and scattering, and considering the impact of seasonal and diurnal changes in solar angle and intensity. This approach aligns with the professional duty of care to design systems that are efficient, reliable, and accurately represent expected performance, thereby meeting regulatory requirements for performance guarantees and investor confidence. It reflects a commitment to evidence-based design and a thorough understanding of the environmental factors influencing renewable energy generation. Incorrect approach is analysis. An incorrect approach would be to assume a constant, idealized solar constant value for all calculations, ignoring the real-world factors that cause its variation. This failure to account for atmospheric effects, orbital mechanics, and solar cycles leads to inaccurate irradiance data. Consequently, energy yield predictions will be flawed, potentially resulting in an undersized or oversized system, both of which are professionally unacceptable and may violate performance standards or contractual obligations. Another incorrect approach would be to solely rely on average irradiance values without considering the variability and extremes. While averages provide a baseline, they do not capture the impact of transient events like cloud cover, dust, or unusual solar activity, which can significantly affect short-term and long-term energy production. This oversight can lead to designs that perform poorly during suboptimal conditions, failing to meet expected output, and potentially leading to financial losses for the client. A third incorrect approach would be to focus exclusively on the theoretical definition of the solar constant, without translating its implications to the specific project location and design parameters. The solar constant is an extraterrestrial value. Its practical application requires understanding how it is modified by the Earth's atmosphere and the specific geographic and temporal context of the solar installation. Neglecting this translation means the design is not grounded in the actual conditions the solar array will experience, rendering the design recommendations speculative and unprofessional. Professional reasoning. When faced with questions about the solar constant and its impact on renewable energy design, a REDP should adopt a systematic process. First, they must understand the theoretical basis of the solar constant. Second, they must research and identify the specific factors that cause variations in the solar irradiance reaching the Earth's surface, including atmospheric composition, aerosols, water vapor, Earth's orbital position, and solar activity. Third, they must determine how these variations translate to the specific project location, considering latitude, altitude, and local climate data. Fourth, they must select and apply appropriate modeling tools and methodologies that can accurately simulate these variations and their impact on energy generation. Finally, they must document their assumptions and the rationale behind their design choices, ensuring transparency and accountability. This structured approach ensures that designs are not only theoretically sound, but also practically robust and compliant with professional standards. Question 6. Analysis of the spectral distribution of solar radiation for a new utility-scale solar PV farm in a region with variable atmospheric conditions. What is the most professionally responsible approach for an REDP to select the solar irradiance data for system design and performance modeling, given the absence of on-site meteorological stations? Option A. Prioritize using the most recent, readily available irradiance data from any source, regardless of spectral resolution or geographical relevance, to expedite the design process. Option B. Utilize a comprehensive, spectrally resolved global solar irradiance database that has been validated for the specific geographic region and accounts for typical atmospheric variations. Option C. Select spectrally resolved irradiance data from a different continent with similar latitude but significantly different prevailing weather patterns. Option D. Employ generic, spectrally uncharacterized solar irradiance data that is widely available and easy to access for the project's general latitude. The correct answer is B. Utilize a comprehensive, spectrally resolved global solar irradiance database that has been validated for the specific geographic region and accounts for typical atmospheric variations. Explanation. This scenario is professionally challenging because the renewable energy design professional, REDP, must select appropriate solar irradiance data for a project site without direct on-site measurements. This requires a deep understanding of how solar radiation varies spectrally and spatially, and how to ethically and effectively utilize available data sources. The REDP must balance accuracy with the practical limitations of data availability and cost, while adhering to professional standards and regulatory requirements for renewable energy design. The correct approach involves utilizing reputable, spectrally resolved solar radiation databases that are validated for the specific geographic region of the project. This method is correct because it aligns with the professional obligation to use the most accurate and relevant data available to ensure the performance and economic viability of the renewable energy system. Regulatory frameworks for renewable energy design, such as those governing grid-tied solar installations, often implicitly or explicitly require designs to be based on reliable, site-specific, or regionally representative irradiance data. Using spectrally resolved data allows for more accurate modeling of photovoltaic (PV) module performance, which is crucial for predicting energy yield and system efficiency, thereby meeting design standards and client expectations. An incorrect approach would be to solely rely on generic, spectrally uncharacterized irradiance data that does not account for atmospheric conditions or spectral variations relevant to the project location. This is professionally unacceptable because it introduces significant uncertainty into energy yield predictions. Such an approach fails to meet the standard of care expected of an REDP, potentially leading to underperformance of the system and financial losses for the client. It also risks noncompliance with design codes or performance guarantees that are predicated on accurate irradiance inputs. Another incorrect approach would be to use irradiance data from a geographically distant location, even if it is spectrally resolved, without proper justification or adjustment for local atmospheric differences. This is ethically problematic as it misrepresents the expected solar resource at the project site. Regulatory bodies and industry best practices emphasize the importance of site specificity in renewable energy design. Using data from a dissimilar location, without a robust methodology for adaptation, demonstrates a lack of due diligence and can lead to designs that are not optimized for the actual site conditions, potentially violating design standards and client trust. Finally, an approach that prioritizes readily available but unverified data over more accurate, albeit potentially less accessible, spectrally resolved data is also professionally unsound. This demonstrates a failure to uphold the principle of professional competence and due diligence. The REDP has an ethical responsibility to seek out and utilize the best available information to inform their design decisions, rather than opting for convenience at the expense of accuracy and reliability. This can lead to designs that do not meet performance expectations or regulatory requirements for energy production. The professional decision-making process for similar situations should involve 1. Identifying the project's specific data requirements based on the technology being designed and regulatory mandates. 2. Researching and evaluating available solar irradiance datasets, prioritizing those that are spectrally resolved and geographically relevant. 3. Assessing the quality, validation, and source of the data. 4. If site-specific measurements are not feasible, selecting the most representative and reliable regional or global datasets, and applying appropriate methodologies for site-specific adaptation. 5. Documenting the data selection process and any assumptions made, ensuring transparency and accountability. Question 7. Governance review demonstrates a need to ensure that all renewable energy design professional (RED) projects accurately assess the solar resource available to tilted photovoltaic arrays. A project engineer proposes using a novel, in-house developed algorithm for calculating solar radiation on tilted surfaces, citing its speed and perceived accuracy. What is the most professionally responsible approach for the RED to take in evaluating this proposal? Option A. Reject the in-house algorithm outright and insist on using a widely published, but potentially less site-specific, solar radiation database that does not account for array tilt and orientation. Option B. Immediately adopt the in-house algorithm due to its reported speed and perceived accuracy, as this will expedite the design process and potentially reduce project costs. Option C. Verify that the in-house algorithm has been independently validated against established meteorological data, and that its methodology aligns with recognized industry standards for solar resource assessment, as may be referenced or implied by the RED regulatory framework. Option D. Proceed with the in-house algorithm, but supplement it with a single, generalized regional solar radiation value to provide a basic cross-check, without detailed analysis of the tilt and orientation impact. The correct answer is C. Verify that the in-house algorithm has been independently validated against established meteorological data, and that its methodology aligns with recognized industry standards for solar resource assessment, as may be referenced or implied by the RED regulatory framework. Explanation. This scenario is professionally challenging because it requires the renewable energy design professional RED to balance the theoretical ideal of solar radiation calculation with the practical constraints of available data and the specific regulatory requirements for reporting and design validation. The RED must ensure that the chosen method for calculating solar radiation on a tilted surface not only accurately reflects the site's potential, but also adheres to the standards mandated by the relevant regulatory framework for renewable energy projects. This involves understanding the limitations of different models and the implications of their use on project feasibility and compliance. The correct approach involves utilizing a widely accepted, validated solar radiation model that is explicitly or implicitly endorsed by the governing regulatory body for RED certification and project approval. This approach is right because it ensures that the design is based on calculations that are understood, verifiable, and consistent with industry best practices as defined by the regulatory framework. Adherence to these established models provides a defensible basis for design decisions, performance predictions, and ultimately, regulatory compliance. The regulatory framework for RED typically emphasizes the use of standardized methodologies to ensure a baseline level of accuracy and comparability across projects, thereby safeguarding public interest and investment. An incorrect approach would be to rely solely on a proprietary, unvalidated software tool that produces results without transparent methodology or clear documentation of its underlying algorithms. This is professionally unacceptable because it bypasses the established standards for verification and validation required by the regulatory framework. Without transparency, it is impossible to assess the accuracy of the calculations or to justify the design decisions to regulatory bodies or stakeholders. This lack of auditable methodology creates significant compliance risks and undermines the professional integrity of the REDP. Another incorrect approach would be to use a simplified, generalized solar radiation value for the region, without accounting for the specific tilt and orientation of the solar array. This is ethically and regulatorily flawed, because it fails to address the core requirement of calculating solar radiation on an tilted surface. The regulatory framework for REDP mandates that designs consider the specific geometry of the installation to accurately predict energy yield. Ignoring the tilt and orientation leads to inaccurate performance estimates, potentially resulting in underperforming systems, financial losses for investors, and a failure to meet project performance guarantees, all of which are contrary to the professional obligations of an REDP. A further incorrect approach would be to select a calculation method based purely on ease of implementation or speed, without considering its suitability for the specific project's location, climate, and the required level of accuracy for regulatory submission. This demonstrates a failure to exercise due diligence and professional judgment. The REDP responsibility extends beyond mere calculation to ensuring that the chosen method is appropriate and robust enough to meet the technical and regulatory demands of the project. Prioritizing speed over accuracy and regulatory appropriateness is a direct violation of professional standards. A professional decision-making process for similar situations should involve a thorough review of the applicable regulatory framework and any associated technical guidelines. The REDP must identify the prescribed or recommended methodologies for solar radiation calculations. If multiple methods are permissible, the REDP should evaluate them based on their accuracy, validation status, data requirements, and suitability for the specific project context. Transparency in methodology and documentation of the chosen approach are paramount for defensibility and compliance. Question 8. Risk assessment procedures indicate that the interpretation of wind data for a proposed wind farm site requires more than just identifying the average wind speed. Considering the potential for environmental and operational impacts, which approach to analyzing and interpreting the site's wind data best aligns with the responsibilities of a renewable energy design professional REDP under relevant regulatory frameworks. Option A. Dismissing any wind data that shows significant deviations from historical averages without further investigation, assuming these are anomalies. Option B. Relying exclusively on generalized wind resource maps for the region without conducting site-specific data validation. Option C. Focusing primarily on the average wind speed across the site as the key metric for determining the project's energy generation potential and overall viability. Option D. Prioritizing the analysis of wind data's temporal and spatial variability, including extreme events and diurnal/seasonal patterns, to assess potential impacts on turbine performance, noise, shadow flicker, and ecological factors, ensuring alignment with specific regulatory impact assessment requirements. The correct answer is D. Prioritizing the analysis of wind data's temporal and spatial variability, including extreme events and diurnal/seasonal patterns, to assess potential impacts on turbine performance, noise, shadow flicker, and ecological factors, ensuring alignment with specific regulatory impact assessment requirements. Explanation. This scenario is professionally challenging because it requires a renewable energy design professional REDP to interpret complex wind data in the context of regulatory compliance and impact assessment, without relying on simple numerical outputs. The challenge lies in understanding the qualitative implications of wind patterns on environmental and operational factors, and how these implications align with established REDP standards and guidelines. Careful judgment is needed to move beyond raw data to a meaningful assessment of potential impacts. The correct approach involves a comprehensive review of the wind data's temporal and spatial variability, considering its implications for turbine performance, noise propagation, shadow flicker, and potential impacts on local ecosystems or bird migration routes. This aligns with the REDP responsibility to design renewable energy projects that are not only technically sound, but also environmentally responsible and compliant with all applicable regulations. Specifically, it requires the REDP to consult and apply the principles outlined in the relevant national or regional regulatory framework governing renewable energy development, which typically mandates thorough impact assessments based on site-specific conditions, including meteorological data. The ethical obligation is to ensure that the design minimizes negative externalities and maximizes the benefits of renewable energy generation, supported by a robust understanding of the site's wind resource and its associated impacts. An incorrect approach would be to focus solely on average wind speeds as the primary determinant of project viability. This fails to account for the critical nuances of wind variability, such as extreme wind events, diurnal patterns, or seasonal shifts, which can significantly influence turbine longevity, grid integration, and the likelihood of exceeding noise or shadow flicker thresholds. Regulatory frameworks often require consideration of a wider range of wind characteristics beyond simple averages to ensure comprehensive impact assessment. Another incorrect approach would be to disregard wind data that deviates from historical norms without a thorough investigation. This overlooks potential changes in climate patterns or localized microclimatic effects that could impact long-term energy production and operational safety. REDP have a professional duty to investigate anomalies and understand their root causes, rather than dismissing them, as this could lead to designs that are not resilient or compliant with future environmental standards. A further incorrect approach would be to rely on generic wind resource maps without validating them with site-specific long-term data. While generic maps provide a starting point, they do not capture the unique micro-siting conditions that can significantly alter wind characteristics. Regulatory approval often hinges on demonstrating that the design is based on accurate, site-specific data, and ignoring this can lead to non-compliance and project delays. Professional decision-making in such situations requires a systematic process. First, clearly define the scope of the impact assessment as per regulatory requirements. Second, gather all relevant wind data, including historical records, meteorological station data, and any available modeling outputs. Third, analyze this data not just for average values, but for its variability, extremes, and patterns, correlating these with potential environmental and operational impacts. Fourth, consult the specific regulatory guidelines and standards applicable to the project's location to understand the criteria for acceptable impacts. Finally, integrate this comprehensive understanding into the design process, ensuring that all potential risks are identified, mitigated, and documented in accordance with professional and regulatory expectations. Question 9. Research into optimizing the water resource utilization for a new pumped hydro storage facility has identified several potential process improvements. Which approach best aligns with the principles of sustainable renewable energy design and regulatory compliance? Option A. Adopting process modifications based on industry best practices from similar facilities in different geographical regions, without specific local hydrological validation. Option B. Implementing process changes that maximize energy generation efficiency, assuming minimal impact on water resources due to the closed-loop nature of the system. Option C. Conducting a detailed hydrological impact assessment that considers the facility's entire water cycle, its interaction with local water bodies, and adherence to all relevant water resource management regulations and permits. Option D. Prioritizing process improvements that offer the most significant short-term cost savings in water management, even if they require less rigorous environmental impact analysis. The correct answer is C. Conducting a detailed hydrological impact assessment that considers the facility's entire water cycle, its interaction with local water bodies, and adherence to all relevant water resource management regulations and permits. Explanation. This scenario is professionally challenging because it requires balancing the optimization of a renewable energy project's water resource utilization with adherence to stringent environmental regulations and the principles of sustainable design. The REDP must ensure that proposed process improvements do not inadvertently lead to negative hydrological impacts or contravene established water management protocols. Careful judgment is required to select an approach that is both technically sound and legally compliant. The correct approach involves a comprehensive hydrological impact assessment that integrates with existing water resource management plans and regulatory frameworks. This approach is correct because it prioritizes understanding the full life cycle of water use and its potential effects on the local ecosystem and downstream users. By aligning process optimization with regulatory requirements and sustainable water management principles, the REDP demonstrates due diligence and ethical responsibility, ensuring the project's long-term viability and environmental stewardship. This aligns with the core principles of renewable energy design, which emphasize sustainability and minimal environmental footprint. An approach that focuses solely on maximizing energy output without considering water resource implications is incorrect. This failure stems from a disregard for regulatory frameworks that govern water abstraction, discharge, and environmental protection. Such an approach risks non-compliance, potential legal penalties, and damage to the project's reputation and the environment. Another incorrect approach is to implement process changes based on anecdotal evidence or limited data without a thorough hydrological study. This is professionally unacceptable, as it bypasses the requirement for evidence-based decision-making and robust risk assessment mandated by regulatory bodies. It can lead to unforeseen negative consequences that are difficult and costly to rectify. Finally, an approach that prioritizes cost reduction over hydrological impact assessment is fundamentally flawed. While cost-effectiveness is important, it cannot supersede regulatory compliance and environmental responsibility. This approach demonstrates a lack of professional integrity and a failure to uphold the ethical obligations of REDP. Professionals should adopt a decision-making framework that begins with a thorough understanding of the project's context, including all applicable regulations and environmental sensitivities. This should be followed by a systematic evaluation of potential process optimization strategies, each assessed for its hydrological implications and regulatory compliance. Prioritizing approaches that demonstrate a commitment to sustainability, regulatory adherence, and comprehensive risk management will lead to sound professional decisions. Question 10. The monitoring system demonstrates that a specific hot rotor speed is consistently 2% below its predicted optimal operational speed under current wind conditions, while other parameters like power output and vibration levels remain within their general acceptable ranges. As a renewable energy design professional, REDP, operating under the specified regulatory framework, which of the following actions best reflects the required professional response? Option A. Adjust the turbine's control system settings to increase rotor speed to match the predicted optimal value, thereby improving efficiency. Option B. Continue normal operation and monitoring, as the deviation is minor and other key performance indicators are within broad acceptable limits. Option C. Conduct a targeted diagnostic analysis of the drivetrain and control system components to understand the root cause of the rotor speed discrepancy before taking further action. Option D. Initiate a full system shutdown and detailed inspection to identify the cause of the rotor speed deviation. Correct answer is D. Initiate a full system shutdown and detailed inspection to identify the cause of the rotor speed deviation. Explanation. This scenario presents a professional challenge because it requires a renewable energy design professional REDP to interpret complex operational data from a horizontal axis wind turbine (HOT) and make a judgment about its performance relative to design specifications and regulatory compliance. The challenge lies in distinguishing between normal operational variations, minor deviations that may not require immediate intervention, and significant issues that could impact safety, efficiency, or regulatory adherence. Careful judgment is required to avoid unnecessary downtime or costly interventions, while ensuring the turbine operates within acceptable parameters and meets all applicable standards. The correct approach involves a comprehensive comparison of the observed operational parameters against the turbine's design specifications and relevant regulatory guidelines for HOT. This approach is professionally sound because it directly addresses the core responsibility of REDP, ensuring the designed and operated renewable energy systems perform as intended and comply with all legal and technical requirements. Specifically, it aligns with the principles of due diligence and professional responsibility mandated by REDP certification, which requires adherence to established design standards and operational protocols. By cross-referencing monitoring data with design documentation and regulatory frameworks, the REDP can accurately assess the turbine's status and determine the appropriate course of action, whether it be continued monitoring, minor adjustments, or more significant maintenance. An incorrect approach that focuses solely on immediate shutdown based on a single, slightly anomalous reading fails to account for the inherent variability in wind conditions and turbine operation. This approach is professionally unacceptable because it can lead to unnecessary operational disruptions and economic losses, without a thorough understanding of the data's context. It bypasses the professional obligation to investigate and analyze before taking drastic measures, potentially violating principles of efficient resource management. Another incorrect approach that involves ignoring the anomaly because it falls within a broad, general tolerance range is also professionally flawed. While some variation is expected, a failure to investigate a deviation, even if seemingly minor, can overlook developing issues that could escalate into significant problems, impacting safety, performance, or leading to regulatory noncompliance. This approach neglects the proactive monitoring and risk assessment expected of REDP. A further incorrect approach that involves adjusting operational parameters to artificially bring the readings within a desired range without understanding the root cause of the anomaly is ethically and professionally problematic. This constitutes a form of data manipulation or misrepresentation, which undermines the integrity of the monitoring system and the REDP professional judgment. It fails to address the underlying issue and could mask a more serious design or operational flaw, potentially leading to future failures and regulatory scrutiny. The professional decision-making process for similar situations should involve a systematic approach. First, understand the specific HOT design parameters and operational envelope. Second, review the relevant regulatory framework for acceptable operational tolerances and reporting requirements. Third, analyze the monitoring data in context, considering wind speed, direction, and other environmental factors. Fourth, compare the observed data against design specifications and regulatory limits. Fifth, consult design documentation and manufacturer guidelines for troubleshooting. And finally, determine the most appropriate course of action based on a comprehensive assessment of risk, performance, and compliance. Question 11. Comparative studies suggest that while various wind measurement techniques exist, the selection of appropriate instruments for a new onshore wind farm development in the UK, governed by the Renewable Energy Design Professional (REDP) framework, presents a critical implementation challenge. Considering the need for data integrity for regulatory approval and financial investment, which of the following approaches best aligns with the professional and regulatory expectations for a REDP? Option A. Utilizing a single, low-cost ultrasonic anemometer mounted on a temporary mast, prioritizing rapid deployment and immediate data acquisition to inform preliminary site assessments. Option B. Relying primarily on publicly available wind maps and historical weather data, with minimal on-site measurement to reduce project development costs. Option C. Installing a series of basic, uncalibrated wind speed indicators integrated into the proposed turbine foundations to gather rudimentary wind data during the construction phase. Option D. Deploying a network of calibrated LiDAR systems for high-resolution wind profiling, supplemented by a limited number of IEC-certified CUP anemometers at key locations to validate LiDAR data and meet regulatory requirements for ground-based measurements. Correct answer is D. Deploying a network of calibrated LiDAR systems for high-resolution wind profiling, supplemented by a limited number of IEC-certified CUP anemometers at key locations to validate LiDAR data and meet regulatory requirements for ground-based measurements. Explanation. Scenario analysis. This scenario presents a professional challenge because the selection of wind measurement techniques and instruments directly impacts the accuracy and reliability of data used for crucial renewable energy project decisions, including site selection, energy yield predictions, and financial modeling. Inaccurate data can lead to significant financial losses, regulatory noncompliance, and reputational damage. The REDP must navigate the trade-offs between cost, accuracy, and the specific requirements of the project and its regulatory environment. The challenge lies in applying theoretical knowledge to a practical, context-dependent decision that has real-world consequences. Correct approach analysis. The correct approach involves selecting a combination of measurement techniques and instruments that are validated by industry best practices and align with the specific requirements of the regulatory framework governing renewable energy projects in the relevant jurisdiction. This typically means prioritizing instruments with a proven track record of accuracy and reliability, such as calibrated anemometers and wind vanes, and considering their deployment in accordance with established standards like those outlined by the International Electrotechnical Commission, (IC), or relevant national bodies. The regulatory framework for REDP likely mandates adherence to such standards to ensure data integrity for permitting, grid connection, and environmental impact assessments. This approach ensures that the collected data is defensible, meets regulatory scrutiny, and provides a sound basis for project design and investment. Incorrect approach is analysis, an approach that relies solely on readily available, uncalibrated, or less sophisticated instruments, such as basic cup anemometers without proper calibration records or wind speed indicators integrated into other equipment, is professionally unacceptable. This fails to meet the accuracy and reliability standards expected for professional renewable energy design. Such an approach risks generating data that is not representative of actual wind conditions, leading to flawed energy yield assessments and potentially non-compliant project designs. It bypasses the due diligence required by regulatory bodies and industry standards, exposing the project and the professional to significant risks. Another incorrect approach would be to prioritize the lowest cost instruments without considering their suitability for the specific site conditions or their adherence to recognized measurement standards. While cost is a factor, it cannot supersede the fundamental requirement for accurate and reliable data. This approach demonstrates a lack of professional judgment and a failure to understand the critical role of wind measurement in the success and compliance of a renewable energy project. It may lead to underperformance, premature equipment failure, or disputes with regulatory authorities. Finally, an approach that ignores the specific environmental conditions of the proposed site, such as turbulence intensity, icing potential, or extreme wind speeds, when selecting measurement instruments, is also flawed. Different instruments have varying sensitivities and operational limits. Failing to account for these site-specific factors can lead to instrument malfunction, inaccurate readings, or premature failure, rendering the collected data useless or misleading. This demonstrates a failure to apply a holistic and site-specific understanding of wind resource assessment, which is a core competency for a REDP. Professional reasoning. Professionals in renewable energy design must adopt a systematic and evidence-based approach to wind measurement. This involves 1. Understanding the specific regulatory requirements and industry standards applicable to the project's jurisdiction. 2. Conducting a thorough site assessment to identify relevant environmental factors that may influence instrument selection and performance. 3. Evaluating available measurement technologies based on their accuracy, reliability, cost, and suitability for the site conditions. 4. Prioritizing calibrated and certified instruments that have a proven track record in the industry. 5. Ensuring that the deployment and maintenance of measurement equipment adhere to best practices and standards. 6. Documenting all measurement procedures, instrument specifications, and calibration records meticulously for regulatory submission and project verification. Question 12. Cost-benefit analysis shows that utilizing a shorter, less intensive on-site measurement campaign and supplementing it with regional mesoscale modeling data could significantly reduce the upfront capital expenditure for a proposed wind farm. As a renewable energy design professional, REDP, what is the most appropriate course of action to ensure regulatory compliance and project integrity? Option A. Proceed with the shorter on-site measurement campaign combined with mesoscale modeling, as the cost savings are substantial and the modeling can provide a reasonable estimate of the wind resource. Option B. Rely primarily on mesoscale modeling data with minimal on-site measurements to achieve the lowest possible upfront cost for the assessment. Option C. Advocate for a comprehensive, site-specific wind measurement campaign of sufficient duration, even if it incurs higher initial costs, to ensure the accuracy and reliability of the wind resource assessment. Option D. Selectively use historical wind data from nearby, but not identical, sites that show higher wind speeds to justify the project's energy production potential. The correct answer is A. Proceed with the shorter on-site measurement campaign combined with mesoscale modeling, as the cost savings are substantial and the modeling can provide a reasonable estimate of the wind resource. Explanation. This scenario presents a professional challenge because it requires a renewable energy design professional, REDP, to balance the immediate financial incentives of a project with the long-term integrity of the wind resource assessment, which underpins the project's viability and regulatory compliance. The REDP must exercise sound professional judgment to ensure that the assessment is not compromised by external pressures, adhering strictly to the established regulatory framework for wind energy projects. The correct approach involves prioritizing the use of a robust, site-specific wind measurement campaign, even if it incurs higher upfront costs. This is justified by the regulatory requirement for accurate and reliable wind resource data to support the design and operational parameters of the wind farm. The REDP professional duty, as outlined in relevant industry standards and potentially codified in licensing regulations, mandates that the assessment be based on the best available scientific and engineering practices. This ensures that the predicted energy yield is realistic, thereby preventing overestimation that could lead to financial misrepresentation, regulatory noncompliance, and ultimately, project failure. Adherence to these standards is crucial for maintaining public trust and the credibility of the renewable energy sector. An incorrect approach would be to rely solely on publicly available, generalized wind data, or to significantly shorten the on-site measurement period to reduce costs. This is a regulatory failure because it deviates from the expectation of site-specific, high-quality data required for a credible wind resource assessment. Ethically, it represents a breach of professional responsibility by potentially misleading stakeholders about the project's true energy production potential. Another incorrect approach would be to selectively use data that favors higher wind speed readings while disregarding periods of lower wind, which is a form of data manipulation. This constitutes a severe ethical and regulatory violation, as it undermines the scientific integrity of the assessment and is a misrepresentation of the wind resource. Professionals should employ a decision-making framework that begins with a thorough understanding of the applicable regulatory requirements for wind resource assessment. This includes identifying the minimum data quality standards, measurement durations, and analytical methodologies mandated by the relevant authorities. The next step is to evaluate the available assessment options against these requirements, considering both technical accuracy and cost-effectiveness. When faced with a conflict between cost reduction and data integrity, the professional must err on the side of accuracy and regulatory compliance, recognizing that the long-term consequences of a flawed assessment far outweigh any short-term financial savings. Open communication with stakeholders about the necessity of robust data collection, even if it increases initial costs, is also a critical component of professional practice. Question 13. Regulatory review indicates that the renewable energy design professional REDP must assess wind characteristics for a proposed wind farm site. The applicable regulations specify a particular set of standardized anemometer deployment and data processing protocols for wind resource assessment. However, preliminary site investigations reveal complex terrain with significant micro-siting variations in wind speed and direction that may not be adequately captured by the prescribed standardized protocols alone. What is the most professionally responsible approach for the REDP to ensure compliance and a reliable wind resource assessment? Option A. Selectively apply only those aspects of the prescribed standardized protocols that align with the preliminary findings, while omitting any data or analysis that suggests a less favorable wind resource. Option B. Disregard the prescribed standardized protocols and solely rely on the most advanced and comprehensive wind modeling software available, irrespective of regulatory mandates. Option C. Supplement the prescribed standardized protocols with additional, site-specific measurement techniques and advanced analytical methods to accurately characterize the complex wind behavior, while clearly documenting the rationale and any deviations from the standard protocols in the final report. Option D. Strictly adhere to the prescribed standardized anemometer deployment and data processing protocols, assuming they are sufficient for all sites within the jurisdiction. The correct answer is D. Strictly adhere to the prescribed standardized anemometer deployment and data processing protocols, assuming they are sufficient for all sites within the jurisdiction. Explanation. This scenario presents a professional challenge because the REDP must balance the practical need for accurate wind resource assessment with the regulatory requirement to adhere to specific, potentially outdated, or overly generalized guidelines. The challenge lies in interpreting and applying these guidelines to a real-world site that may exhibit unique wind behavior not fully captured by the prescribed methods. Careful judgment is required to ensure compliance without compromising the integrity and reliability of the wind resource assessment, which directly impacts project feasibility and investment decisions. The correct approach involves a nuanced interpretation of the regulatory framework, recognizing that, while specific methodologies are mandated, the underlying intent is to achieve a robust and representative understanding of the wind resource. This approach prioritizes site-specific data collection and analysis that aligns with the spirit of the regulations, even if it requires supplementary or more advanced techniques to accurately characterize complex wind behavior. The regulatory justification stems from the principle of due diligence and the professional obligation to provide accurate assessments. Ethical considerations demand that the REDP does not misrepresent the wind resource due to an overly rigid adherence to potentially insufficient guidelines. An incorrect approach of strictly adhering to a single, potentially simplistic, prescribed method without considering site-specific complexities would fail to meet the regulatory intent of ensuring a reliable assessment. This could lead to an inaccurate representation of the wind resource, potentially resulting in underperformance or overestimation of energy yield, which has significant financial and environmental implications. Another incorrect approach of disregarding the regulatory guidelines entirely in favor of the most advanced or preferred personal methodology would be a clear breach of regulatory compliance, exposing the project and the professional to legal and professional sanctions. A third incorrect approach of selectively applying parts of the guidelines that support a desired outcome, while ignoring those that suggest a more conservative assessment, constitutes professional misconduct and a failure of ethical responsibility. Professionals should employ a decision-making framework that begins with a thorough understanding of the applicable regulatory framework. This involves identifying the core requirements and the underlying objectives. Subsequently, a detailed site assessment should be conducted to understand the specific wind characteristics. The REDP must then critically evaluate how the prescribed regulatory methods apply to the site's conditions and identify any potential discrepancies or limitations. Where the prescribed methods are insufficient, the REDP should explore supplementary or alternative techniques that are scientifically sound and can be justified within the broader regulatory intent. Documentation of the rationale for any deviations or supplementary analyses is crucial for demonstrating due diligence and compliance. Question 14. Consider a scenario where a renewable energy design professional REDP is tasked with assessing the annual energy production for a proposed wind farm. Initial site assessments indicate an average annual wind speed that is slightly lower than the speed range for which the selected wind turbine model is typically optimized according to the manufacturer's datasheet. The REDP must determine how to accurately represent the expected power output for regulatory submission and client financial modeling. Which of the following approaches best aligns with professional standards and regulatory expectations for this situation? Option A. Disregard the manufacturer's power curve and develop a new power curve based solely on the limited site-specific wind speed measurements collected to date. Option B. Calculate the total annual energy production by multiplying the average wind speed by the power output at that average speed, as indicated on the manufacturer's power curve. Option C. Adjust the manufacturer's power curve by proportionally reducing the power output across all wind speeds based on the difference between the measured average wind speed and the manufacturer's optimal range. Option D. Apply the manufacturer's certified power curve directly to the measured site-specific wind speed data, acknowledging any potential deviations in the final energy yield assessment report. The correct answer is D. Apply the manufacturer's certified power curve directly to the measured site-specific wind speed data, acknowledging any potential deviations in the final energy yield assessment report. Explanation. This scenario presents a professional challenge because it requires the renewable energy design professional REDP to balance the theoretical ideal of wind power generation with the practical realities of site-specific wind conditions and regulatory compliance. The challenge lies in accurately representing the expected energy yield of a wind turbine installation when actual measured wind speeds deviate from the manufacturer's specifications or initial site assessments. Making an inaccurate assessment can lead to significant financial implications for the client, potential regulatory noncompliance, and damage to the professional's reputation. Careful judgment is required to ensure that the power output predictions are both realistic and defensible under the relevant regulatory framework. The correct approach involves utilizing the wind turbine manufacturer's power curve, which is a standardized document detailing the expected power output at various wind speeds, and applying it to the site-specific wind speed data. This approach is professionally sound because it directly references the manufacturer's certified performance data, which is typically derived from rigorous testing and forms the basis for many regulatory approvals and financial models. The REDP responsibility is to interpret and apply this data correctly to the measured wind conditions at the project site. This aligns with the ethical obligation to provide accurate and reliable information to clients and stakeholders, and it adheres to the implicit regulatory expectation that performance predictions are based on established manufacturer specifications and site-specific measurements. An incorrect approach would be to arbitrarily adjust the manufacturer's power curve based on a subjective interpretation of site conditions without a clear, documented methodology or regulatory basis. This fails to uphold the professional standard of using verifiable data and could lead to over- or underestimation of energy production, potentially violating contractual obligations and regulatory requirements for accurate reporting. Another incorrect approach would be to solely rely on the average wind speed without considering the variability and distribution of wind speeds throughout the year. Wind turbines do not produce power linearly with wind speed. Their power output is dictated by the power curve. Ignoring this curve and simply scaling output based on average wind speed would lead to a fundamentally flawed energy yield assessment, misrepresenting the project's true potential and violating the principle of providing accurate technical assessments. A further incorrect approach would be to disregard the manufacturer's power curve entirely and attempt to derive a new curve based solely on limited site data. This is professionally unsound, as it bypasses the established and certified performance characteristics of the equipment. Regulatory bodies and financiers rely on manufacturer-provided power curves as a benchmark. Deviating from this without robust, independently validated data and a clear regulatory pathway for such deviation would be a significant professional and ethical lapse. The professional decision-making process for similar situations should involve a systematic review of all available data, including manufacturer specifications, site-specific meteorological data, and relevant regulatory guidelines. The REDP must prioritize the use of certified data and apply it rigorously to the specific project context. When discrepancies arise, the professional should seek clarification from the manufacturer, consult relevant industry standards, and ensure that any adjustments or interpretations are transparent, well-documented, and justifiable under the governing regulatory framework. Ethical considerations demand honesty and accuracy, while regulatory compliance necessitates adherence to established procedures and reporting standards. Question 15. Market research demonstrates that clients often seek to minimize the upfront cost of photovoltaic (PV) systems. As a renewable energy design professional (REDP) operating under Australian regulations, you are tasked with designing a residential PV system. Your client has expressed a strong desire to reduce the initial investment. Considering the regulatory framework and the need for a safe and reliable system, which of the following design approaches best adheres to professional and regulatory obligations? Option A. Prioritize PV modules and inverters with the absolute lowest purchase price, regardless of their specific certifications or suitability for Australian climatic conditions, to meet the client's immediate budget constraints. Option B. Design the system with PV modules and inverters that have significantly lower efficiency ratings than readily available compliant alternatives to reduce the overall system size and therefore the initial cost. Option C. Choose PV modules and inverters that are certified for use in regions with significantly different environmental or grid connection regulations, as long as they appear to offer a substantial cost saving. Option D. Select PV modules and inverters that are certified to meet relevant Australian standards, e.g., as/NZS 5033, as/NZS 4777, and have robust manufacturer warranties, even if they represent a moderate upfront cost, to ensure long-term performance and compliance. The correct answer is D. Select PV modules and inverters that are certified to meet relevant Australian standards, e.g., as/NZS 5033, as/NZS 4777, and have robust manufacturer warranties, even if they represent a moderate upfront cost, to ensure long-term performance and compliance. Explanation. Scenario analysis. This scenario is professionally challenging because it requires balancing client cost-saving desires with the fundamental regulatory obligation to design a PV system that is safe, reliable, and compliant with all applicable standards. The temptation to compromise on component quality or oversizing to meet a tight budget is a common pitfall. A RED must exercise sound professional judgment, prioritizing long-term system performance and safety over short-term financial gains for the client, while also demonstrating a thorough understanding of the relevant regulatory framework. Correct approach analysis. The correct approach involves selecting PV modules and inverters that meet or exceed the minimum performance and safety standards mandated by the relevant Australian standards, e.g., as/NZS 5033 for installation, as/NZS 3000 for electrical safety, and as/NZS 4777 for grid connection. This includes verifying that the chosen components have the necessary certifications and warranties to ensure their longevity and reliable operation within the specified environmental conditions. This approach is correct because it directly aligns with the RED professional responsibility to design systems that are compliant with Australian regulations, ensuring the safety of persons and property and the integrity of the electrical grid. Adhering to these standards prevents potential system failures, reduces the likelihood of costly repairs, and upholds the reputation of the renewable energy industry. Incorrect approaches analysis. Selecting PV modules and inverters based solely on the lowest upfront cost, without rigorous verification of their compliance with Australian standards or their long-term performance characteristics, is an incorrect approach. This failure constitutes a breach of professional duty and regulatory noncompliance, as it prioritizes cost over safety and reliability. Such a decision could lead to premature component failure, reduced energy generation, and potential safety hazards, all of which violate the spirit and letter of Australian electrical and renewable energy regulations. Choosing PV modules and inverters that are certified for use in different climatic regions or with different grid connection standards, even if they appear to offer a cost advantage, is also an incorrect approach. This demonstrates a lack of due diligence in understanding the specific requirements of the Australian market and its regulatory framework. Using non-compliant components can lead to grid instability, safety risks, and failure to obtain necessary approvals for system operation, directly contravening Australian standards. Opting for PV modules and inverters with significantly lower efficiency ratings than what is technically feasible and cost-effective for the site, solely to reduce the initial system size and thus the overall cost, is another incorrect approach. While oversizing can be a design consideration, deliberately choosing underperforming components without a clear technical justification and without considering the long-term energy yield and client expectations can be seen as a misrepresentation of system capabilities and a failure to meet the client's underlying need for reliable renewable energy generation. This can also indirectly lead to noncompliance if the system fails to meet performance benchmarks or grid connection requirements due to inadequate component selection. Professional reasoning. When faced with a client's cost-saving objectives, a RED should first engage in a transparent discussion about the trade-offs between upfront cost and long-term performance, reliability, and regulatory compliance. The professional decision-making process should involve 1. Thoroughly understanding the client's budget and energy needs. 2. Identifying all applicable Australian standards and regulations for PV system design and installation. 3. Researching and specifying components that meet or exceed these standards, prioritizing certified products with reputable warranties. 4. Presenting the client with design options that clearly outline the cost, performance, and compliance implications of different component choices. 5. Documenting all design decisions and justifications, particularly when deviating from standard best practices or when cost is a significant driver. 6. Seeking client sign-off on the final design, ensuring they understand the implications of their choices. Question 16. The investigation demonstrates that a client is seeking to minimize upfront capital expenditure for a new rooftop solar photovoltaic system and has presented a proposal featuring solar panels from a lesser-known manufacturer with a significantly lower unit cost compared to established brands, despite offering a seemingly comparable warranty period. As a renewable energy design professional, RED, what is the best practice approach to evaluating this proposal? Option A. Advise the client that only solar panels from established, premium manufacturers should be considered, regardless of cost, to ensure optimal system performance and warranty coverage. Option B. Proceed with the design using the proposed panels, focusing solely on the electrical and structural integration, and deferring detailed warranty analysis to the client after system installation. Option C. Conduct a comprehensive review of the lesser-known manufacturer's warranty terms and conditions, scrutinizing clauses related to performance degradation, labor costs for replacement, and dispute resolution, while also verifying compliance with all relevant national and local electrical codes, building standards, and grid interconnection requirements. Option D. Accept the proposal based on the lower unit cost and the stated warranty period, assuming that basic product certifications are sufficient to guarantee long-term performance and reliability. Correct answer is C. Conduct a comprehensive review of the lesser-known manufacturer's warranty terms and conditions, scrutinizing clauses related to performance degradation, labor costs for replacement, and dispute resolution, while also verifying compliance with all relevant national and local electrical codes, building standards, and grid interconnection requirements. Explanation: this scenario is professionally challenging because it requires a renewable energy design professional REDP to balance the client's desire for immediate cost savings with the long-term performance and safety requirements mandated by regulatory frameworks. The REDP must exercise sound professional judgment to ensure the proposed solar energy system is not only cost-effective, but also compliant and reliable. The correct approach involves a thorough evaluation of the solar panel manufacturer's warranty terms and conditions, cross-referenced with relevant national and local building codes and electrical safety standards. This ensures that any proposed system design adheres to minimum performance guarantees and safety protocols, preventing potential future liabilities for both the client and the designer. Specifically, this approach aligns with the ethical obligation of an REDP to prioritize client safety and system integrity, as well as the regulatory requirement to design systems that meet established performance and safety benchmarks. The REDP must ensure that the chosen components and design will perform as expected over their lifespan and will not pose a safety risk, which is a fundamental tenet of professional engineering practice. An incorrect approach would be to solely prioritize the lower upfront cost of the solar panels without a comprehensive review of their warranty. This fails to meet the professional responsibility to ensure long-term system viability and could lead to significant unexpected costs for the client if the panels underperform or fail prematurely, and the warranty is inadequate or voided by improper installation or design. This also neglects the regulatory imperative to design systems that are reliable and meet expected performance standards, potentially leading to non-compliance with energy generation targets or grid interconnection requirements. Another incorrect approach is to assume that all solar panels meeting basic certification standards are equivalent in terms of long-term performance and warranty coverage. While certifications ensure a minimum level of safety and quality, they do not guarantee the robustness of a manufacturer's warranty or the actual long-term degradation rates of the panels. Relying solely on basic certifications without delving into warranty specifics and manufacturer reputation is a failure to conduct due diligence, which is a core ethical and professional requirement for an REDP. A further incorrect approach would be to disregard the client's specific site conditions and energy needs in favor of a generic, low-cost solar panel solution. This overlooks the fundamental principle of renewable energy system design, which is to tailor solutions to the unique requirements of the application. Failing to consider factors like shading, local climate, and the client's energy consumption patterns can lead to a system that underperforms, even with high-quality panels, and may not meet the client's objectives, thereby failing to uphold the professional duty to provide effective and appropriate design solutions. The professional decision-making process for similar situations should involve a systematic risk assessment. This includes identifying potential technical, financial, and regulatory risks associated with different design choices. The REDP must then evaluate these risks against established professional standards, ethical guidelines, and applicable regulations. Transparency with the client regarding the trade-offs between upfront cost, long-term performance, warranty coverage, and regulatory compliance is paramount. The ultimate decision should be based on a holistic evaluation that prioritizes safety, compliance, and the client's long-term interests, rather than solely on immediate cost savings. Question 17. The analysis reveals that for a new solar farm project in a region experiencing consistently high ambient temperatures, 2 PV module options exhibit comparable peak efficiency ratings under standard test conditions, STC. However, their temperature coefficients for power output differ. Which approach to module selection is most aligned with professional best practices for ensuring optimal long-term energy yield and system reliability? Option A. Select the module with the higher peak efficiency rating at STC, irrespective of temperature coefficients. Option B. Select the module with the lower cost per watt, prioritizing initial project budget over performance characteristics. Option C. Select the module with the lower negative temperature coefficient for power output. Option D. Select the module with the higher negative temperature coefficient for power output, as it indicates a greater potential for power generation under ideal conditions. The correct answer is C. Select the module with the lower negative temperature coefficient for power output. Explanation: scenario analysis. This scenario presents a professional challenge in selecting PV modules for a renewable energy project where performance under varying temperature conditions is critical. The challenge lies in accurately interpreting PV module datasheets, specifically understanding the implications of temperature coefficients on energy yield and system design. Misinterpreting these values can lead to underperformance, increased operational costs, and failure to meet project energy generation targets, potentially impacting client satisfaction and regulatory compliance. Correct approach analysis. The correct approach involves prioritizing PV modules with lower negative temperature coefficients for power output. This is because a lower negative coefficient indicates that the module's power output will decrease less significantly as its temperature rises. For a renewable energy design professional REDP, operating under the specified regulatory framework, this approach aligns with the professional duty to design systems that are efficient, reliable, and perform as expected under real-world operating conditions. The regulatory framework implicitly requires designs that maximize energy yield and minimize performance degradation, which is directly addressed by selecting modules with superior thermal performance characteristics. This ensures the system's long-term economic viability and contributes to meeting renewable energy targets. Incorrect approaches analysis. An incorrect approach would be to prioritize modules solely based on their peak efficiency rating at standard test conditions, STC, without considering their temperature coefficients. While high efficiency is desirable, it does not guarantee optimal performance in elevated operating temperatures, which are common for PV modules. This approach fails to account for the real-world operating environment and can lead to a system that underperforms significantly, violating the REDP responsibility to deliver a functionally sound design. Another incorrect approach would be to select modules with higher negative temperature coefficients, assuming that any module with a good STC efficiency is acceptable. This overlooks the direct impact of temperature on power output, leading to a design that is susceptible to substantial energy loss in warmer climates or during peak sun hours. This demonstrates a lack of due diligence in understanding module performance beyond ideal conditions and can result in a system that does not meet performance expectations, potentially leading to contractual disputes or regulatory noncompliance. Finally, an approach that disregards temperature coefficients entirely and focuses only on cost per watt would be professionally unsound. While cost is a factor, it should not supersede the technical performance and long-term reliability of the chosen components. Ignoring critical performance parameters like temperature coefficients can lead to a system that is cheaper initially but more expensive to operate and less productive over its lifespan, failing to meet the REDP obligation to provide a cost-effective and high-performing solution. Professional reasoning. When faced with selecting PV modules, a REDP should adopt a holistic evaluation process. This involves first understanding the project's specific environmental conditions, particularly expected operating temperatures. Then, critically analyze module datasheets, giving significant weight to temperature coefficients for power, voltage, and current, in addition to STC efficiency. The decision-making process should prioritize modules that demonstrate the least degradation in performance as temperature increases. This systematic approach ensures that the chosen modules will contribute to achieving the project's energy generation goals reliably and efficiently, adhering to professional standards and regulatory expectations for renewable energy system design. Question 18. System analysis indicates that a proposed solar photovoltaic installation is to be located at a significant altitude, and the design team is considering the impact of atmospheric conditions on energy yield. Which of the following considerations best reflects a professional approach to accounting for the influence of air mass on solar irradiance for this project? Option A. applying a uniform, generic correction factor to all irradiance calculations to compensate for atmospheric attenuation, without specific consideration for air mass or module technology. Option B, relying solely on standard global horizontal irradiance, GI, data for the region, assuming that typical weather patterns will adequately account for any atmospheric effects. Option C, disregarding the impact of air mass as a secondary factor, focusing primarily on module efficiency ratings and inverter performance. Option D, adjusting the predicted solar irradiance values based on the specific spectral response of the chosen PV modules and the expected range of air mass values at the site to ensure accurate energy yield predictions. The correct answer is D, adjusting the predicted solar irradiance values based on the specific spectral response of the chosen PV modules and the expected range of air mass values at the site to ensure accurate energy yield predictions. Explanation: this scenario is professionally challenging because the renewable energy design professional, REDP, must balance the theoretical impact of air mass on solar irradiance with practical, site-specific conditions and regulatory compliance. The challenge lies in accurately assessing how atmospheric conditions, beyond simple distance from the sun, will affect the energy yield of a proposed solar installation, and then translating this into design decisions that meet performance expectations and regulatory standards without over-engineering or under-delivering. The correct approach involves understanding that air mass is a critical factor influencing the spectral distribution and intensity of solar radiation reaching the Earth's surface. For a REDP, this means considering how variations in atmospheric composition, altitude, and the angle of the sun, which directly relates to air mass, will affect the performance of photovoltaic PV modules. Specifically, higher air mass values, e.g., at sunrise/sunset or higher altitudes, lead to a longer path through the atmosphere, causing increased scattering and absorption of solar radiation, particularly in the shorter wavelengths. This can reduce the efficiency of PV modules designed for a standard spectrum. And 5. A REDP must account for these effects when performing energy yield assessments and selecting appropriate module technologies or system configurations to ensure the system meets its projected performance targets under realistic operating conditions, as stipulated by industry best practices and potentially by local building codes or performance guarantees. This aligns with the professional duty to design safe, efficient, and reliable renewable energy systems. An incorrect approach would be to solely rely on standard irradiance values without considering the impact of air mass on spectral content and intensity. This overlooks a fundamental aspect of solar resource assessment and can lead to inaccurate energy yield predictions, potentially resulting in a system that underperforms its guaranteed output. Such an oversight could violate contractual obligations and professional standards of care, as it fails to account for predictable environmental influences on system performance. Another incorrect approach would be to assume that all PV modules are equally affected by air mass variations. Different PV technologies have varying spectral responses. Ignoring these differences and applying a blanket correction factor for air mass would be an oversimplification and could lead to suboptimal design choices. This demonstrates a lack of detailed technical understanding and a failure to apply best practices in PV system design, potentially leading to inefficient or non-compliant installations. Finally, an incorrect approach would be to dismiss the impact of air mass as a minor factor, assuming it is adequately covered by general weather data. While general weather data is important, air mass is a specific atmospheric optical parameter that directly influences the quality and quantity of light reaching the PV cells. Failing to specifically address its impact, especially in regions with significant altitude variations or where performance guarantees are critical, is a failure to conduct a thorough and professional design analysis. The professional decision-making process for REDP should involve a systematic evaluation of all relevant environmental factors, including but not limited to air mass. This requires consulting reliable meteorological data, understanding the spectral characteristics of different PV technologies, and applying appropriate modeling tools to predict system performance under various atmospheric conditions. When in doubt, consulting with atmospheric scientists or utilizing advanced simulation software that explicitly models air mass effects is advisable. The goal is to ensure that the design system is robust, reliable, and meets all performance and regulatory requirements. Question 19. To address the challenge of accurately assessing site-specific solar resource for a new utility-scale solar farm development, which approach to solar radiation measurement and instrument selection best aligns with the regulatory framework for renewable energy design professionals in the specified jurisdiction. Option A. Rely exclusively on long-term average solar irradiance data from a nearby meteorological station, without any on-site measurements, for all design calculations. Option B. Utilize a pyranometer that has a current calibration certificate traceable to a National Metrology Institute and is certified to meet ISO 9060 standards for spectrally flat response, ensuring its placement minimizes shading and is representative of the plane of array. Option C. Use a pyranometer that was last calibrated 5 years ago, as the calibration interval is not explicitly defined in the project's preliminary guidelines. Option D. Employ a photodiode-based light sensor that has been used for indoor lighting measurements, as it is readily available and can provide a general indication of sunlight intensity. The correct answer is B. Utilize a pyranometer that has a current calibration certificate traceable to a National Metrology Institute and is certified to meet ISO 9060 standards for spectrally flat response, ensuring its placement minimizes shading and is representative of the plane of array. Explanation. Scenario analysis. This scenario presents a professional challenge because the accuracy and reliability of solar radiation measurements directly impact the design, performance prediction, and economic viability of renewable energy projects. Inaccurate data can lead to undersized or oversized systems, resulting in financial losses, reduced energy generation, and potential noncompliance with performance standards. The REDP must exercise careful judgment to select appropriate measurement techniques and instruments that align with regulatory requirements and industry best practices to ensure project success and stakeholder confidence. Correct approach analysis. The correct approach involves selecting a pyranometer that is calibrated according to recognized international standards, such as ISO 9060, and ensuring its placement adheres to guidelines that minimize shading and environmental interference. This is crucial because regulatory frameworks for renewable energy design often mandate the use of calibrated and traceable instruments for performance verification and grid connection approvals. Adherence to standards like ISO 9060 ensures that the instrument's measurements are accurate, repeatable, and comparable to those taken by other certified devices, thereby meeting the stringent data quality requirements for project design and reporting. Incorrect approaches analysis. Using a pyranometer that has not been recently calibrated or whose calibration is not traceable to national or international standards is a significant regulatory and ethical failure. This practice undermines the integrity of the collected data, making it unreliable for design calculations and performance guarantees. It violates the implicit requirement for due diligence and the use of fit-for-purpose equipment mandated by most renewable energy regulations. Employing a pyranometer that is not designed for outdoor, long-term solar radiation measurement, such as a photodiode-based sensor intended for indoor light sensing, is another critical failure. Such instruments lack the necessary spectral response, temperature compensation, and weatherproofing to provide accurate and stable readings under varying environmental conditions. This directly contravenes the principle of using appropriate technology for the intended application, leading to data that is not representative of actual solar irradiance and thus unsuitable for project design. Relying solely on historical weather data without on-site solar radiation measurements for critical design decisions, especially for projects requiring precise energy yield assessments, is also professionally unacceptable. While historical data provides a general understanding, it does not account for site-specific microclimates, shading from nearby structures or vegetation, or the actual diurnal and seasonal variations in irradiance. Regulatory bodies often require site-specific measurements to validate energy production models and ensure compliance with performance targets, making historical data alone insufficient for critical design phases. Professional reasoning. Professionals in renewable energy design must adopt a systematic approach to solar radiation measurement. This begins with understanding the specific regulatory requirements for the project's jurisdiction, which often dictate the acceptable accuracy classes of instruments and the need for traceable calibration. The next step is to identify suitable instrument types, e.g., pyranometers, that meet these specifications and are designed for the intended application. Crucially, all instruments must undergo regular calibration by accredited laboratories, and calibration certificates must be maintained. Site assessment for optimal instrument placement, considering factors like shading, tilt, and orientation, is also paramount. Finally, data validation and quality control procedures should be implemented to ensure the collected measurements are reliable and representative of the site's solar resource. Question 20. The review process indicates that a proposed flat plate collector system for a new commercial building is being evaluated. The design team has presented two options, one with a slightly lower initial cost but requiring more frequent specialized cleaning, and another with a higher initial cost but designed for minimal, standard maintenance. The client has expressed a strong preference for minimizing upfront expenditure. As the RED, what is the most professionally responsible approach to advise the client regarding the selection of the flat plate collector system? Option A. Advise the client to defer the decision on the flat plate collector system until a separate, in-depth operational and maintenance training program for their facility staff can be developed and implemented. Option B. Strongly advocate for the higher cost, low maintenance option, providing a detailed lifecycle cost analysis that demonstrates its long-term economic benefits and reduced operational burden, even if it exceeds the client's initial budget preference. Option C. Propose a hybrid approach that incorporates elements of both options, perhaps suggesting a phased maintenance plan or alternative cleaning methods to balance cost and operational demands. Option D. Recommend the lower cost option, emphasizing the immediate savings and assuming the client will manage the specialized maintenance as needed. The correct answer is D. Recommend the lower cost option, emphasizing the immediate savings and assuming the client will manage the specialized maintenance as needed. Explanation. The scenario presents a common challenge in renewable energy projects, balancing the technical performance of a system with the practical constraints and expectations of stakeholders, particularly concerning the long-term operational efficiency and maintenance of flat plate collectors. The professional challenge lies in ensuring that design decisions, while technically sound, also align with the operational realities and the client's understanding of the system's capabilities and responsibilities. This requires a nuanced approach that goes beyond mere technical specification to encompass clear communication and realistic expectation setting. The correct approach involves a thorough assessment of the proposed flat plate collector system's operational requirements, including maintenance schedules, potential for degradation, and the client's capacity to manage these aspects. This aligns with the principles of responsible design and professional practice, emphasizing long-term sustainability and client satisfaction. Specifically, it adheres to the spirit of the Renewable Energy Design Professional REDP framework, which implicitly requires designs to be not only functional, but also maintainable and operable by the end user or their designated representatives, ensuring the intended energy generation is achieved over the system's lifespan. This proactive engagement with operational realities prevents future disputes and ensures the project's success. An incorrect approach that focuses solely on initial installation cost and immediate energy output overlooks the critical aspects of long-term operation and maintenance. This failure to consider the full life cycle of the flat plate collectors can lead to suboptimal performance, increased operational expenses for the client, and potential noncompliance with performance guarantees if maintenance is neglected. Ethically, it represents a lack of due diligence and a failure to adequately inform the client of all relevant factors influencing the project's success. Another incorrect approach that prioritizes the most advanced, high-efficiency collector technology without a corresponding assessment of the client's ability to maintain it is also professionally unsound. While high efficiency is desirable, it often comes with more complex maintenance requirements. If the client lacks the technical expertise or resources for this specialized maintenance, the system's performance will inevitably degrade, negating the initial efficiency advantage. This demonstrates a disconnect between design and operational reality, failing to meet the client's actual needs and capabilities. A further incorrect approach that relies on generic performance data without site-specific considerations for factors like shading, soiling, or extreme weather conditions is also problematic. Flat plate collector performance is highly sensitive to environmental factors. Failing to account for these specific site conditions in the design and operational planning can lead to significant discrepancies between expected and actual energy generation, impacting the project's economic viability and the client's trust. Professional decision-making process in such situations should involve a comprehensive risk assessment that includes technical, economic, and operational factors. It requires open communication with the client to understand their capabilities and limitations regarding system operation and maintenance. The RED professional must then propose solutions that are technically sound, economically viable over the system's lifecycle, and operationally feasible for the client, ensuring that all stakeholders have a clear and realistic understanding of the project's requirements and expected outcomes.